In this lesson, we'll look at the sine law. We've seen in previous lessons that we can solve or find the unknown sides and angles of right angle triangles using the sine, cosine, and tangent ratios. Now, to solve non-right angle triangles, we have to take a different approach and either use the sine law, which we'll look at in this lesson, or the cosine law, which we'll look at in the next lesson. To solve any triangle, you need to be given at least 3 pieces of information, either 2 angles and a side, 2 sides and an angle, or 3 sides. You need to be given at least 1 side because if you're only given 3 angles and no sides, there's an infinite number of similar triangles that are consistent with that information. You could scale that triangle up and down, keeping the same angles and changing the side lengths, and those would all be consistent with the given information. Let's look at how the sine law is stated. First, let's remind ourselves of how we name the vertices and sides of a triangle. We use capital letters to name the vertices, capital A, capital B, and capital C, and we use lowercase letters to name the sides, lowercase a, lowercase b, and lowercase c. And we place the same letter on opposite sides and angles. So lowercase a is the side opposite uppercase or capital A. I'm going to call these a side angle pair because they're opposite each other and they share the same letter as part of their name. Now the sine law is stated in one of 2 ways, either with the sine ratios on the top of the fractions given or at the bottom. Let's look at the first one. So one way of stating the sine law is sine A over A is equal to sine B over B is equal to sine C over C. And you'll only ever use these 2 parts at a time, not all 3 parts. So for example, you might use those 2 parts at one time. And if you knew sine A, and if you knew B, you could solve for sine B, and therefore for angle B. You can also put the sides on the top and the angles and their sine ratios on the bottom. You're going to want to choose either this version or this version depending on what your unknown is. It's easier to do the algebra if you put your unknown in the numerator. Let's take a look at an example. Here's the information given for this triangle, and I'm asked to solve for side length b to 1 decimal place. Now the first thing we might want to do is figure out angle A. We know that angle A is going to be equal to 180 degrees minus 66 degrees minus 52 degrees, because all the angles have to sum to 180, and that means that angle A is equal to 62 degrees. Let's put that on the diagram. Now the sine law tells us that A over sine A is equal to B over sine B, and I'm putting lowercase b, or side length b, in the numerator because that's what I want to solve for. Now I can plug in all the information that I have. Side length A is 2.5. I've worked out angle A, so angle A is 62 degrees. Sine 62 goes in the denominator. Careful, it's not just 62 degrees that goes in the denominator, but sine of 62. B is my unknown, and sine of B is sine of 52 degrees. Now if I rearrange and solve for B, I get B is equal to 2.5 sine 62 over sine 52. And plugging that into your calculator, making sure your calculator is in degree mode, you get approximately B is equal to 2.2, and our units was meters. So that's how you'd use the sine law to solve for a side length. Notice that to use the sine law, you have to take 4 pieces of information, and only one of them is going to be unknown. In that case, this was B. I say that you need to be given 1.5 side angle pairs. This is 1 side angle pair there, and the other one is here. We've got half of it in the 52 degrees. So to use the sine law, you need to be given 1.5 side angle pairs. Here's another example. This time we're being asked to solve for an angle. So because we're being asked to solve for an angle, we're going to put the sine ratios in the numerator. So the sine law tells us that sine B over B is equal to, and this time we're going to use C sine C over C. Plugging in the values that we have, we get sine B, which is our unknown, over side length B is 7, is equal to sine of 76 degrees over 10. Multiplying across, we get sine B is equal to 7 sine 76 over 10. Now the most common mistake that people make at this point is they just evaluate this and think that they found angle B, but that's not angle B, that's the sine ratio of angle B. So you have to go one more step. You can either evaluate this in your calculator and then take the inverse sine, but you need to be careful that you keep enough decimal places. And another way of doing it is just to take the sine inverse and let your calculator do everything. So you want to find the sine inverse of sine 76 over 10. And if you let your calculator do all of this, putting in brackets so that it evaluates it appropriately, you don't have to worry about the rounding. And you should get that b is approximately equal to 42.8 degrees. So that's an introduction to the sine law. Now we need to learn about a particular circumstance called the ambiguous case of the sine law. The ambiguous case of the sine law arises when the information that you're given is two sides in an angle, and the order that they're given in as you go either clockwise or counterclockwise around the triangle is side, side, angle. And we'll take a look at what that means. If that's the way the information is given to you, then it's possible that there is just one triangle consistent with that information, but it's also possible that there's no triangles that would work with that, or that there might be two triangles. So we're going to work through how the ambiguous case arises, and then we'll look at some problems. Now, to see how it arises, we're going to set up this situation. We're going to imagine we have an angle A that's 30 degrees, as shown here, and a side length of a triangle B that's 10 units in length. And we're going to vary the length of side A, the side opposite angle A. So in this diagram, this would be A here. Vertex B isn't shown, but would be wherever this line hits this line here. Now, in this circumstance, we've got a side length A that's too short to make a triangle. If this angle is fixed at 30 degrees and this is 10 units long, the way it's drawn here, this line segment isn't long enough to touch this line, and therefore no triangles are formed. We'll look in a moment in what length this needs to be to form a triangle. So I want you to imagine that this line segment is like a pendulum. Because this angle is not fixed, this can swing back and forth, and it's going to do so trying to reach down here to complete a triangle that has 30 degrees over here. If we make that line segment longer, so we've taken this and extended it down this way, when we make it just long enough to touch the dotted line, it'll form a right-angled triangle, because the shortest distance between point C and point B is going to make a 90-degree angle with this line down here. Again, imagine that this is a pendulum swinging back and forth. If you imagine it swinging either to the right or to the left, it's going to be too short to hit this bottom line. So the shortest possible length that this can be is when this is a right angle. Now, if that's a right angle and this is 10 units in length here, then we can ask, well, what's the length of A? In other words, what's the shortest length that A can be to make a triangle? Well, if it's a right angle triangle, we know that sine 30 degrees is equal to opposite A over the hypotenuse 10. And rearranging that, we get 10 sine 30 is equal to A. We know from our special triangles that sine 30 is a half, so that means that A is equal to 5 units long. In other words, when A is equal to 5 units, we get exactly one triangle, and that triangle is a right-angled triangle. Now, if we go back to the previous example, that means to form no triangles at all, A would have to be less than 5. So that is going to give us no triangles at all. Now let's continue making A longer. If we make A longer than this, so imagine it extends down to here, now if it swings back and forth, it would cut this line that forms the 30-degree angle in two places. In other words, you'd get a picture like this. Again, imagine these are pendula swinging back and forth. So this is the same length as this. Both of them are length A, and again, this is 10. Now, how long is this? Well, if A was 5, it would have made a right-angled triangle, as we saw in the previous example. So here, A has to be greater than 5 units in length in order to hit twice. It's also, however, got to be less than 10 units in length, because if you imagine A, which is either here or here, swinging back and forth and being 10 units in length, when it got to this side, it would be superimposed exactly over this point. And so you'd get a picture that looked like this with no triangle at all. So A has to be shorter than 10 units in order to make this leftmost triangle. Now you need to be a bit careful about where the triangles are here. We want a triangle with side length 10 and angle 30 degrees. So that means that this is one triangle consistent with the information we're given, and this is the other triangle. This isosceles triangle in here is not one of the triangles we're concerned with. We want a triangle consistent with the information of side length 10 angle 30 degrees and the other side being A. So that's a circumstance where if A is less than 10 but greater than 5, and remember we got 5 from working out the side lengths in our right angle triangle, now we have two triangles that are consistent with the information that we're given. Now if we keep making A longer, now if this is longer than 10, let's say A was 11 or 12, as we just saw in the previous example, it's no longer going to be able to make that leftmost triangle. It's no longer going to be able to make this triangle, because when we swing A from here to here, we're not going to get it here making a triangle. It's actually going to end up on this side. If it were longer than 10, it would miss here, come over this way, and although it's still making a triangle, there's no 30-degree angle in that triangle. It would make this angle, which would be 150 degrees. So in this case, when A is greater than 10, or in fact when it's equal to 10, because if it's equal to 10 it will lie exactly on this line, then we only get one triangle again. So we see that there are 4 different circumstances. To review then, if A is shorter than it needs to be to make a right angle triangle, it's going to form no triangles at all. We can work out this 5 by working out the length required to make a right angle triangle. Using the sine ratio, if A in this example is equal to 5, we get one right angled triangle. If we make it a bit longer, we can now make a triangle this way or this way. And that's what we see here. Here's one triangle, here's another triangle. That happens when A is between 5, the shortest length required, and 10, the length of the side given. And then if we make it even longer, if we make it longer than 10 or equal to 10, we only get one triangle again. If we start with angle A being obtuse, like 120 degrees, instead of acute, like the 30 degrees we were using before, then the situation is simplified and there are only 2 possibilities. So if this is 120 degrees and this is still 10, then if line segment A, or side A, is less than or equal to 10, then we won't get any triangles at all, because if it's equal to 10, it will be such that when it swings this way, it'll only touch the bottom line when B and A line up exactly. We'll get a line segment instead of a triangle. And if it's shorter than 10, then it just won't hit this bottom line at all as it swings back and forth. So if A is less than or equal to 10, we'd get 0 triangles in this situation. And if A is greater than 10, then we would only get one triangle, as shown in the diagram. Here, if this is 10 and if A is longer than 10, it would hit this bottom line, but if we imagine it swinging this way, it would only hit the line if we extended it again on this side, and this angle is not 120 degrees. It's 60, so that's not consistent with the information we're given. Okay, let's take a look at an example of the kind of question that you could be asked based on these concepts. So we want to know how many triangles we can construct using the given information, either 0, 1, 2, or infinite. And the infinite number of triangles answer would come if we were given 3 angles but no sides. As we talked about in the introduction, we could scale that triangle up or down and get an infinite number of similar triangles. That's not what we're given. We're given side lengths, so we can rule that answer out immediately. If we draw a picture of the information that we're given, we call this angle A, and we label that with 50 degrees. Side B has length 9, side A has length 4. And the question is, does this triangle exist at all? Are there perhaps more than one triangle that are consistent with this information? So the easiest way to sort this out is to figure out what the minimum length this side would have to be in order to make a right angle triangle. Now I'll point out that this is a side-side angle triangle, so this is the kind of triangle that we were talking about in the introduction to the ambiguous case, where you have this side being the pendulum. This side is fixed length, this angle is fixed length, so you can imagine this 4 as being the pendulum side. So if we work out how long this side A would have to be, how long the pendulum would have to be in order to make one right-angled triangle, I'm going to call this A minimum. And this is still 50 degrees and 9. Now we know that sine 50, because this is a right-angled triangle, is equal to A minimum, the opposite side, over 9, the hypotenuse. And solving for A minimum, we get that it's equal to 9 sine 50. Putting that into your calculator, you should get that A is approximately equal to 6.9. meters. Now, that means that in order to form one right-angled triangle, with this 50-degree angle and this 9 being fixed, the pendulum side would have to be 6.9 meters at the least. Now, the information that we're given is that A is 4, so that means it's too short, and therefore there are 0 triangles. So 4 is less than 6.9, or the given value of A is less than the minimum value of A required. Therefore, there are no triangles consistent with this information. Let's look at another type of problem that you could be given. This one's perhaps more typical. You're just asked to solve for an angle given some information. So if we draw the picture, angle A is 32 degrees, side A is 5.5 meters, side B is 9.5 meters. And we'll notice again that this is a side-side angle triangle. The order in which the information is given to us, going either clockwise or counterclockwise, is side-side angle. So this is an ambiguous case, and I've drawn it in much the same way as I drew the previous examples. Here 5.5 is our pendulum side. Because this angle and this side length are fixed, this 5.5 length side we can imagine swinging back and forth and trying to hit the line at the bottom to make a triangle. Now, we don't actually need to go through the work of working out how many triangles are possible, because as we go through the calculations for the question, the answer will become apparent to us. But you could do that to start off with if you wanted to. You could go through the previous process that we did and work out whether 5.5 is long enough, or whether it is long enough to only make one triangle, or whether it's going to make 2 triangles. So if we just go ahead and solve this, though, without working that out, setting up the sine law, we get sine B over 9.5 is equal to sine 32 degrees over 5.5. And rearranging, we get that sine B is equal to 9.5 sine 32 over 5.5. Therefore, B is equal to the inverse sine of that. And it's easiest just to let your calculator do all the work and put it all in one step. Now, if you do that, you'll get an answer from your calculator that B is approximately equal to 66 degrees. So that means that this angle here, as we've drawn it, would be 66 degrees. But remember that there are 2 values between 0 and 180 degrees that will have the same sine value, the same sine ratio. If we think of the unit circle, remember that sine represents the y-coordinate. Between 0 and 180 degrees, this point has the same y-coordinate as this one. There's going to be 2 values for angles between 0 and 180 that have the same sine ratio. That means there's actually 2 answers for this. We can think of it being this one over here, the 66 degrees, and this one over here, which is going to be equal to 180 minus 66 degrees, which is equal to 114 degrees. So that means that the other possible answer for angle B is 114 degrees, and that will arise if we swing this pendulum over this way, so that the 5.5 is here and this angle is 114 degrees. Now, if it were the case that there were only one triangle, we would have ended up getting that B was equal to 90 degrees. That would be our one right-angled triangle. And if there were no triangles at all, then what would have happened in this step is we would have gotten an answer that when we plugged it into our calculator would give us an error. In other words, we'd be taking the sine inverse of something, for example, greater than 1, and the calculator wouldn't be able to do it. That would indicate that there are no triangles at all consistent with the information that we were given. And we could then go back and just double check that we hadn't made an error by going through the kinds of calculations that we did before to see how many triangles there were. So that's the ambiguous case. It arises when the information we're given about a triangle is a side length, and an angle in that order, going either clockwise or counterclockwise.